The primary unit of management in Palette is the cluster profile. Cluster profiles make up the various layers that we call packs. Cluster profiles are declarative and reusable templates that can be used to build and manage clusters any number of times. Cluster profiles are one of three types: full, infrastructure, or add-on. Full profiles are made up of both infrastructure and add-on packs. Infrastructure profiles are made up of the four core components needed to define a Kubernetes cluster: operating system, Kubernetes distribution, container network interface, and container storage interface. These infrastructure packs are typically not portable and will be made up of different components depending on the cloud or infrastructure type. Add-on profiles are the additional packs needed to operationalize a cluster. However, these packs are typically portable and can be run across most Kubernetes clusters. Here we are defining the infrastructure profile for a basic EKS cluster: the OS with Amazon Linux, the Kubernetes layer, the network with the AWS VPC CNI, and the storage with the Amazon EBS CSI. We'll save this cluster profile, and now we are ready to deploy this profile to a cluster. We will pick the cluster name, cloud account, region, SSH key pair, desired networking type, node pool configuration, and instance types. Now we wait for the cluster to provision. First the control plane, then the various layers start to complete. Finally, the worker nodes will provision and become healthy. Once the worker nodes are joined, the final steps take place and the cluster health checks pass, allowing the cluster to show fully online. The finished cluster is defined by cluster profile packs, and changing the packs will trigger the automation to update the cluster to match the changes. In this case, we will create a new version of the cluster profile and update the Kubernetes pack in the infrastructure profile to a higher version, and save the changes. We will then go into the cluster profile settings of the running cluster and change the version of the cluster profile used to the new version. We will accept the changes and start the process. In just a short time, the cluster will update the control plane and perform a rolling update to the worker nodes in a technique that we call a repave. Certain actions and updates to infrastructure packs will trigger a repave, where we perform graceful replacement of cluster nodes for zero-touch and zero-downtime cluster updates and upgrades. Next, we'll build an add-on profile to apply sample applications to the cluster. We'll then go into the running cluster and attach the add-on profile. Cluster profile version updates can be applied to clusters, and the changes will be reconciled. In cases of failure, the cluster profile will show an error and supply logs. Where supported, the cluster profile version can be updated to the previous version, giving administrators the ability to roll back to a known good working state. We'll then download the kube config and look up the new namespace created by the sample application deployment. Now we'll delete the namespace, and after some time, the reconciliation loop will reapply the changes to match the desired state set in Palette. Palette has a built-in routine to automatically reconcile and update the configuration of resources it manages. This means if a change is made to those resources outside of the Palette toolset, Palette will correct this, and the risk of configuration drift is reduced dramatically. Here we'll attach a policy to the node role in AWS. Since the role is managed by Palette, a reconciliation loop will remove the additional policy from the role. In addition to managing clusters and cluster resources via the UI, Palette has a rich set of APIs administrators can interact with. We provide a Golang SDK, a Terraform provider, and a crossplane provider. Let's look at how programmatic access via the Terraform provider can simplify operations at scale. Here, we will use the Terraform provider to create 11 new projects along with a set of users that will be assigned a role only containing their approved permissions in the project they are assigned to. In this example, we are using Boolean variables to enable the modules. Now we'll create 9 tenant-level cluster profiles that can be used to create clusters across multiple cloud environments and are shared as a standard across the 11 projects. Now we'll create cloud accounts for the tenant. Multiple cloud accounts are created for each cloud type we'll use, but VMware service accounts and edge hosts were created ahead of time. Finally, we can create clusters using the cluster profiles and cloud accounts. In just over 2 minutes, the Terraform run creates 110 clusters across 30 unique regions in 8 cloud targets: AWS IaaS, AWS EKS, GCP IaaS, GCP GKE, Azure IaaS, Azure AKS, VMware, and Edge. Once the Terraform run is completed, the cluster provisioning automation leveraging Cluster API will take over for Terraform, and the clusters will begin to come online around the 30-minute mark. By the 45-minute mark, most of the 110 clusters are online and ready to use.